Hi everyone, welcome to this session. I'm Vasudev Lal, a principal AI research scientist at Intel Labs, and I'm really excited to talk to you about the work that my team, the cognitive AI team at Intel Labs, has done on multimodal RAG systems developed on Intel Gaudi AI accelerators. So our team's work is highly inspired by how we believe humans have developed a high cognitive understanding of the world around us. As humans, we use all of our senses to understand the world around us. So for example, for the concept of an apple, we understand the sound that is made if someone bites into an apple. We also understand the color, the texture of an apple. And we also associate certain facts with the concept of an apple. We understand that apples are rich in minerals and vitamins. We all know the famous saying that an apple a day keeps a doctor away, and so on. Similarly, in our cognitive AI team, over the past 3 years, we have been building multimodal AI models that are able to connect through concepts that are expressed in different modalities. I like the joke, a dog is a dog is a dog, whether the concept of a dog is expressed in language, which might be English or any other human language, or if the concept of a dog is expressed in images or videos or cartoons. So with that motivation, we have been training multimodal foundation models on hundreds of Gaudi AI accelerators in the Intel Tiber AI Cloud. I have linked here two of these models, the Bridge Tower model and latent diffusion model for 3D that we have open sourced, and let's see these models in action. So for example, for the Bridge Tower model, this is a multimodal transformer model that's been trained on 512 Gaudis, and in this application, this model can accept any video URL and a user query, and the model will try to retrieve a frame from that video that best describes that user query. So for example, for this user query of a man with a beard walking, the model will execute this user query on this video database, and it will go to frames that best match this particular query. Let's look at one more query. Intel Labs written on a metal plate. So in this case also, the model will go retrieve the frame that best matches this particular user query. Now, what is interesting is that this particular model has not been trained for such an OCR task, an optical character recognition task. But when we train these multimodal transformer models on hundreds of Gaudi AI accelerators over millions of image-text pairs, then we have found that these OCR characteristic emerges in the model. Now, our team is also interested in building foundation models that can create new multimodal content. So for example, we have trained a custom diffusion model on Gaudi that we call LDM 3D or latent diffusion model for 3D. This model can take language prompts and generate 360 immersive scenes like we can see in the visuals here. This custom diffusion model generates the RGB image and corresponding depth map. The depth map is used to simulate a 360 view of the scene. So while a lot of our team's work is in the open domain, where we publish detailed technical papers in top AI conferences, and we open source our implementations, we open source our model checkpoints, we also collaborate with Intel's customers and partners for proprietary foundation models. So for example, on this slide, I show how our team collaborated with Boston Consulting Group, BCG, to build enterprise-grade, secure LLM trained generative AI platform, all developed on Intel Gaudi-based cluster. Now, since we are very interested in pushing the state-of-the-art in research, I have a short list of some of the publications from our team. We've been very excited that 4 of the publications from our team have won an equivalent of a Best Paper award in the last 2 years, and these span across computer vision focused conferences like CVPR and NLP focused conferences like ACL. As a practicing AI researcher myself, I like to follow Hugging Face's daily paper list to keep up with the latest and greatest papers that are coming out almost every day. And we've been very proud that 7 papers from our team have featured in this list over the last year or so. And earlier this year, one of our papers, which was called Neuroprompt, it was focused on how we can automate prompt engineering for large language models, was featured as the top story in IEEE Spectrum, showcasing how LLMs have really progressed to the point that a lot of prompt engineering that's required for getting the best results out of LLMs can be automated. We can train LLMs in a certain way to do that kind of prompt engineering. So our work is made possible by massive AI clusters that are powered by Intel Gaudi AI accelerators in the Intel Tiber AI Cloud. Here we have 2 of our team members next to the AI cluster we work on. Let's now take a quick video tour of one of the data centers. Nothing can be more exciting than getting to work on state-of-the-art AI clusters. Intel is one of the only companies that is full stack. Having access to this scale of compute is necessary to push the state of art in AI today. Yeah, so what we just saw was one of the data centers that powers our Intel Tiber AI Cloud, this one particularly in Scottsdale, Arizona. And we are very excited that our team and along with customers were able to scale out foundation model trainings on such massive AI clusters. Now, over the last few months, our team has been extremely interested in helping bring about a transition from text-only LLMs to multimodal LLMs. We know a lot of the world's data exists in the form of multimodal documents. This includes videos, it includes slides, PDF documents that include charts and figures and so on. So to truly unlock intelligence, and especially for enterprise AI, where a lot of documents have such multimodal content, it is essential that LLMs are able to comprehend such multimodal data. So we have been training a class of multimodal LLMs that are known as the Lava architecture, where an image encoder is connected to an LLM. So one example of one such model is a multimodal version of Llama 3. In fact, on the very day that Meta released their Llama 3 model, our team fired up a 4-node Gaudi 2 cluster in the Intel Tiber AI Cloud, and we trained a multimodal version of Llama 3. So in this model, we can give it an image, we can do question answering over an image, and from the responses we see here, we can see that the model is very good at understanding contents in an image. So our team has open sourced checkpoints of these multimodal LLMs trained on Gaudi 2 AI clusters. And here I show 2 examples. We've open sourced a Lava Gemma model, which is a multimodal version of Google's Gemma model. And we've also open sourced a Lava Llama 3 model, which is a multimodal version of Meta's Llama 3 model. As you can see, these models are present under the Intel organization in Hugging Face. Apart from releasing model checkpoints, we have also open sourced training recipes for these models on our team's GitHub. We are really hopeful that these training recipes can provide a starting point for developers to develop their own models using Intel Gaudi AI accelerators. Like many teams, our team also cross-operates between Intel Gaudi-based AI clusters as well as competition's GPU-based clusters. So we are very interested in maintaining a hardware vendor agnostic training recipe. we would ideally like that our training recipes, which are written in PyTorch, is the exact same PyTorch code that can run on both Intel Gaudi AI accelerators as well as competitors' GPU. So on this slide, I have a link to our source code for training the Lava Gemma model, where it's the exact same source code that runs on Gaudi AI accelerators as well as competition's GPU products. You can see here that there's a very minor change required in the logic of the import libraries. If we detect CUDA, for example, then the source code will go import NVIDIA specific libraries. If CUDA is not detected, then the source code will go import Gaudi specific libraries, but the rest of the PyTorch code is identical. And this is how other teams and other enterprises can make hardware vendor agnostic training recipes. So what can these multimodal LLMs do? So here I want to show an application that's powered by one of our multimodal LLMs that powers a multimodal RAG chatbot. So in this chatbot, we are going to execute a highly technical question. We're going to ask this chatbot, how do tri-gate fins work? And what we've also done is that we've indexed videos related to Intel technology, and what this chatbot has done is it has retrieved such a video, and using that video, it's answering this particular query. So in this video, we can see Intel Senior Fellow Mark Board describing Intel's tri-gate technology, and our chatbot uses the context of this video to answer this particular query. Let's try one more query. So let's try this query. What percentage of renewable energy is Intel planning to use? And here we see that the model has retrieved the snippet of President Biden in our Arizona factory talking about Intel's commitment to using 100% renewable energy.
Leading-edge chips by the end of the decade. And right here in the United States, Intel is committed to net zero greenhouse gas emissions by 2040, and using 100% renewable electricity to power these fabs. And there's more, because this isn't just about investing in America.
As we all understand, RAG chatbots really help LLMs be able to use external knowledge, knowledge that is recent, that the model might not be trained upon. But as we also know, a lot of the world's information is not just text only. So this shows how we can use our multimodal foundation models to power these multimodal RAG chatbots that can retrieve video segments, they can retrieve multimodal documents that have images and figures, and use the context in those documents to answer user queries. So this is a brief architecture diagram of such a system, and you can see that it is being powered by two multimodal foundation models. So an embedding model, for which we use the bridge tower model that I have previously described, and a large vision language model, or LVLM, in this block diagram, for which we use Lava-like models. So first, if we have enterprise multimodal data that consists of images or multimodal documents, we ingest these documents using our embedding model to populate a vector database. Then if we have a user query, we again process the user query through the embedding model, and we'll retrieve a video segment that can best help answer the user query. Then this retrieved video segment is given to our large language model, which is implemented by Lava, to help answer the user query. Now, if you're really interested in how to build such multimodal RAG applications, my team teamed up with Andrew Ng and his fantastic team at deeplearning.ai to make this free course available on how to develop multimodal RAG applications that will allow you to chat with videos. In this particular course, you will learn how to pre-process videos, how to transcribe videos, how to create descriptions of videos if a transcription is not possible, how to ingest all of this multimodal data into a vector database, how to instantiate multimodal LLMs and how to put together the entire architecture diagram that was on my previous slide to make a multimodal RAG chatbot. So if you're interested in this technology, please go ahead and check out this course. And this entire course is powered by multimodal foundation models that are hosted on an Intel Gaudi 2 AI cluster in our Intel Tiber AI Cloud. Now, in my team, we're very interested in training these large-scale foundation models on Intel AI Cloud, and typically we'll train these models on hundreds of Gaudi AI accelerators. But we are also very interested in porting these models to devices like Intel's AI PC, where inference of these models can take place at scale. So here I show one example where we have the multimodal semantic search that I just showed earlier running completely on Intel's AI PC. And this is one example where using Intel technologies, we can train these foundation models at scale using Intel's data center products, large-scale AI clusters that are powered by Intel Gaudi AI accelerators coupled with Intel Xeon head nodes. But once these models are trained, for mass deployment, we can convert these models using OpenVINO to a form that can be easily run on Intel's AI PC offerings. My team has also partnered with Hugging Face to showcase how multimodal transformers can be trained on Intel Gaudi 2 AI accelerators and how the performance, the training throughput of training these vision language models on Intel Gaudi 2 platform is faster than competition's leading GPUs. I've shown that we've open sourced many of these Lava models, and we are also very interested in scaling up the size of these models. So in this slide, we see a Lava model being scaled up to about 70 billion parameters. Now at 70 billion parameter, the model will not fit a single Gaudi 2 AI accelerator card. So for doing this training, we make use of full 3D parallelism. So we split the weight of the model across different Gaudi 2 cards. We split the layers of the model also across different Gaudi 2 cards. And we also split the training examples across different Gaudi cards. So these 3 degrees of parallelism, which are called tensor parallelism, pipeline parallelism, and data parallelism, is necessary to train models at this scale. And on the chart, we can see that as we scale up the model size from 7 billion parameters to 70 billion parameters, we see a better pre-training convergence loss. We see that the masked language modeling task, which is informed by the visual input, the image, it converges to lower values and it converges faster as we scale up the model size from 7 billion to 70 billion parameters. Now for training these models, we use a variety of software platforms that have been developed around the Intel Gaudi software ecosystem. So I want to talk a little bit about how my team trains these models at scale using a couple of training regimes. So for example, Intel and Hugging Face have jointly developed a library that's called Optimum Habana. And using this library, we can easily scale up training to hundreds or thousands of Gaudi AI accelerators. So in this chart, we can see that there are very few code changes required to port over a Hugging Face training recipe that works on competition's GPU to Intel's Gaudi accelerator. And then I also show an example of a sample Kubernetes manifest file to run distributed jobs. And Intel and Hugging Face have created these scripts. For example, the Gaudi spawn.py script shown here, which can easily help deploy this training workload over multiple Gaudi accelerator cards or servers. And there are command line arguments to engage, for example, the media pipe data loader, which will engage hardware-accelerated data loading on Gaudi AI accelerators. Another framework that my team uses quite a bit for doing large-scale training is PyTorch Lightning. And again, Intel and PyTorch Lightning have collaborated to make sure that Gaudi is well supported in the PyTorch Lightning ecosystem. So here we can see that from the Lightning libraries, we can import certain modules, especially the HPU accelerator. And when we set up the trainer class for the accelerator, we just need to specify the HPU accelerator. So that's pretty much the only change we need for taking any standard PyTorch training recipe, PyTorch Lightning training recipe, and to get it running on Intel's Gaudi platform. Again, I show an example of a manifest Kubernetes file that can help scale out this training to multiple nodes. Here, for example, to 128 Gaudi nodes. And then on the right-hand side, we show the convergence of one of our multimodal transformers as we effortlessly scale to 512 Gaudi AI accelerators. Now, we've reached the stage where multimodal foundation models are moving from research to production. And in this era, it is really important to have methods that we can use to probe and measure social biases in these models, and also to develop methods where we can reduce the amount of social biases in these multimodal foundation models. So in a work that we just published at CVPR earlier this year, we show how we can do this by creating large synthetic data sets of counterfactual image-text pairs where we systematically vary a social attribute. So for example, we can see here that we are very systematically varying either the perceived race or a perceived gender of the people in these synthetically created images. While we keep a lot of aesthetic similarity in this group of synthetically created images. So once we create a set of such images, we can probe if multimodal foundation models have any specific biases specific to people that belong to a specific perceived gender or a specific perceived race. And we also show in our paper that if we create the synthetic data set and then we fine-tune multimodal foundation models on such data sets, we can reduce the bias and the social bias in these models by about 20%. I also want to briefly mention about our work with the neuroscience team at UT Austin that was featured in a paper at NeurIPS last December, where we demonstrate the first ever modality transfer in human brain data. So we have a flowchart here on the right where we can see that we had human subjects listening to stories in a fMRI scanner. Now, as they were listening to stories, their brain activation data was captured by the fMRI scanner, and we also then processed the same story using one of the multimodal transformer models developed in our team. Then from the embeddings of the multimodal transformer model, we could predict the brain data for these human subjects that were listening to the story. Now that itself was very exciting, but what was even more exciting is that when we changed the modality the modality that these human subjects were experiencing in the fMRI scanner. So when we switched from these people listening to stories to watching a movie, the same brain encoding model that was trained just to predict the human brain response when the stimulus was a story is able to predict the human brain response when the stimulus is movies. Now, this will only work if both the human brain and the multimodal transformers developed in our brain have these A-modal concepts. So, if we encounter the concept of a dog either in a story or in a movie, it activates similar patterns in the human brain, and it activates similar patterns in the multimodal transformer models that we've developed in our team. So this should go back to our original thesis that there are these amodal concepts, that there are these concepts that are informed by knowledge in various modalities, in language, in video, in speech, and the goal of a truly cognitive AI system is that that a model is able to thread through concepts that intersect all of these modalities. So we are very excited that we are able to show this in human brain data, and we are able to do this by training models on really large clusters that are powered by Intel Gaudi AI clusters on millions of examples of multimodal data. And we are very excited to show the art of what is possible as we now scale out to Gaudi 3 clusters in the coming year. So with that, I want to thank you all for your time, and thank you so much for attending this session.